before spring break, we talked a bunch about AGDA, and of course there's a module on AGDA that's due this Wednesday, and I hope that I guess in previous times I've taught this class, we spent longer in AGDA, and there were some like more difficult things that I took off the module, or like there were multiple modules I think in previous semesters on AGDA. So hopefully the stuff that's on the module, my intention is that it's not too bad. So definitely take advantage of the ways that AGDA kind of helps you keep track of things, right? So do stuff incrementally, use the holes, use auto, whatever you can do to help you. And some of it is just about like getting the definitions right in the first place. So like, for example, one of the problems says, write down a data type that encodes this idea. Once you get that data type correct, then it asks you to prove some stuff about it. But actually proving stuff about it should not be too hard. It's just like pattern match, fill in this, do that, right? Definitely ask for help if you're stuck. So we're going to kind of shift emphases, and there's kind of a couple reasons. I mean, number one, this was always the plan, actually, that we were going to kind of do some AGDA and then kind of come back to Haskell stuff. But I've even, like, over spring break, I kind of redid the schedule in terms of what I was planning to cover for the rest of the semester. I think I realized that the first time I taught this class, it just so happened the students that were in the class were very excited about like theoretical stuff, like I am, and that was fun. And I think I'm realizing that, and it's just different, right? It's not to say like better or worse. It's just like I think y'all are more motivated by more practical things, it seems to me. And so there still will be theory, and we're going to talk about practical stuff and kind of like how theory informs that, or how we use theoretical stuff to kind of do practical things. But I think there'll definitely be more emphasis on like writing actual Haskell code and learning about some practical stuff that we can do with Haskell, as opposed to writing explanations about proofs about the lambda calculus or whatever. So that's kind of where we're going. So what we're going to do today, so essentially, I want to spend some time talking, we'll basically spend this week talking about sort of more practically how do people make use of stuff in the Haskell standard libraries, and like when you're writing real world Haskell code, some of the ways that you do that might be different than the ways that you would write imperative code. And also different than the ways that we've been doing exercise and problem sets so far. So in particular, we spent a lot of time writing recursive functions, right? So, we implemented, like we wrote, for rows trees, you wrote like a fold rows and a map rows, right? And we wrote like list map, and when we, like on the homework where we did stuff with the look and say sequence, right? Your look and say function was recursive, and you wrote a helper function that was recursive. Like you're writing all these recursive functions, which makes sense because Haskell doesn't have loops. So the only thing you can do is recursion, okay? But I don't know if I've said this before. Doesn't matter if I have or not. But it may surprise you to learn that in the real world, Haskell programmers rarely write recursive functions. So the stuff that you all were doing on those modules, in some sense, was kind of artificial, because number one, it's just an artificial problem. But number two, the way that we went about solving it is maybe not the way that an experienced Haskell programmer would have done it. It's the way I expected you to do it, because that's what we were practicing and learning. So how is that? How is it possible? Like how could Haskell programmers not write recursion very much? There's no loops, so they're not writing loops. Okay, the answer is they're actually working at an even higher level. They're using stuff in the standard library, for example, like map, right, and lots of other stuff that does recursion for them. So part of what we're going to do is just look through the standard library and learn about more things that are in there. You know, and you see them, and as you practice using them, you start to notice these patterns, and you're like, oh, this seems like I could do this with a zip and a map and a something, and you put those pieces together. And then partly we're going to think about this idea called wholemeal, what some people call wholemeal programming. The basic idea is to kind of work on the level of entire data structures all at once, rather than thinking about, oh, I have this data structure, so, you know, like in Java, if you have a data structure and you want to do something with it, you're going to write a loop and, like, you know, go over each thing in the data structure. You're not typically going to have like a function that does something on the entire data structure. Whereas in Haskell, it's much more typical to say, I have this whole data structure, I'm going to take the data structure and transform it through a series of steps, like transform it into a different data structure, and then like do something to everything all at once. And then, you know, so thinking about transforming whole data structure is not about doing stuff to individual items. So working at the level of entire data structures at once, not at the level of individual items. Okay, so as a first example, I'm going to write some. So let's say we want to keep only the items in a list that are less than 10, and double the remaining items. Okay, this is, for the sake of having a simple example, this is pretty artificial, right? But so, like as an example, if I have 1, 4, 19, 7, 32, 65, right? I want that to turn into like, well, I'm only going to keep the things that are less than 10, and I'm going to double them. So 2, 8, 19 I'm going to get rid of. 7 I'm going to keep and double. 14, 32 I'm going to get rid of. 16 I'm going to get rid of. 8 is going to double. And 5 is going to double. Does that make sense? So, and just as a point of comparison, here's how we might do this in Java. We might write something like this. So let's say I have like my, int array nums. And then I would say like, for int I equals 0, I is less than 9. Well, I've got to make like, let's say like nums2 is where I'm going to put, let's say I've already like initialized them, I don't know, but, or you know what, let's just say I have, I plus plus, and then I'm going to say, if nums I is less than 10, then I'm going to double it and put it in nums2. So I'm going to say like nums2, you know what, yeah, we're going to make this. Nums2 dot add nums I times 2. Like this, okay? Makes sense? So looks familiar, right? This is like, I'm sure you've written code like this before. So there's a few things about this that I don't like. Maybe you don't like these things either. Maybe you've never thought about that you don't like them because you didn't know there was an alternative. But one thing is that you have to write this loop that goes over each thing in the list, and you have to have this variable I, even though our English description didn't say anything about I. It just said, keep the items in the list that are less than 10 and double the remaining items. But in order to do that, I have to make up this new variable I that's going to like count through an index, and I don't really care about the indices. That's just this device I need in order to access all the elements of nums, right? And while that brings in all sorts of potential, like I could misspell the name of the variable, I could like, maybe I already have something named I, maybe I like, get the index wrong. I could put like a less than or equal to instead of less than. I could start it at 1 instead of 0. And yeah, you don't make those mistakes anymore, but especially as it gets a little more complicated, it's very easy to make that kind of like off. I mean, I'm sure I have, and I'm sure all of you have, like, made that kind of mistake where you were off by 1 in a loop, and it like went outside the bounds of the array or something, right? That's annoying because that has nothing to do with the problem you're trying to solve. That's just like an incidental detail. The other thing is that it's kind of mixing up. There's two things that are happening. You're keeping only certain items, and you're also doubling the remaining items. But like the code for that is all kind of mixed up all together here, right? It's like we're checking here if it's less than 10, and we're multiplying by 2 here. It would be, and if you have like more steps that have to happen, as you add more and more steps, the coding here just gets more and more complicated. And it's not obvious, like, what are all the separate things that are happening. So problems. So one was that we have to talk about index I, and that easy to get on. Whoop. And then 2 was the various steps are all mixed up. Okay. Well, and maybe here's another point about when I say that code is mixed up. What's the problem with that? Well, let's say I have some other code where I need to keep only the items in a list that are less than 10, but then do something else. I can't reuse any of this code. I just have to write it over from scratch because, like, here, the fact that I'm like keeping only things less than 10 is mixed up with the fact that I'm multiplying things by 2, and if I can't just like easily reuse one part of it as other. So now we could solve problem 2 by saying, okay, let's make an intermediate array list. First, we're going to loop through nums and just put everything less than 10 in this intermediate array list. And then we're going to have another loop where we go through that array list and multiply everything by 2 and put that in yet another array list. Or we could just like multiply everything by 2 in place. But that's kind of annoying, and actually it's pretty inefficient because we're generating this extra array list. We got to like allocate memory for it and stuff. And Java won't get rid of that for us. It's just like, so everyone does it this way and would tell you to do it this way for efficiency. Even though kind of like in terms of code reuse and separating out different things, it might be nicer to have an intermediate array list where you put stuff in first and you do the next step. So of course, as you expect, I'm about to tell you how Haskell solves all these problems first. So now, we could, and maybe I'll write this first just to illustrate. We could, but we shouldn't, do things essentially the same way, like this. So we could say something like, do stuff, takes a list of int and gives a list of int, and do stuff, I'm going to pattern match and say, well, if it's empty, I'm returning empty, and if it's cons, I'm going to have a little guard and say, well, if x is less than 10, then I want to keep it and say, like, 2 times x cons with do stuff x's, and, otherwise, if x is not less than 10, I'm going to just say do stuff x's. So this is, it's not exactly the same, right? But it's similar-ish. At least I don't have to have I, right? But I do have to like name the individual elements of the list x, and I've got to I'm going through the things one by one, and the code to like check whether it's less than 10 and multiply by 2 is kind of mixed up together again, right? But there is a better way. It doesn't have to be uncommon. Stuff 2. So I'm doing two things. So I'm going to take this entire list, and first, I want to only keep the things that are less than 10. Right? And there's a standard function called filter. I don't know if we've seen this before. So let me, you know, if I showed you all Google, you've seen this? Okay. So that's how I found this. And even if you didn't know it was named filter, right, you could search by type. Because we could say, well, okay, what I want to do is I want to take a list. I want to take a list as input and give a new list as output. But according to some predicate, where I tell it like which things to keep and which things not to keep, right? So you might be able to come up with this type that says, okay, well the predicate is going to be a function from A to bool. It says, should I keep this A or not? And then it takes a list of things you list it. So if you can come up with that type, you can find this filter. So filter applied to a predicate in a list returns the list of those elements that satisfy the predicate. Okay, so the predicate we give it is which things we're supposed to keep. So for example, filter odd 1, 2, 3 is 1, 2. So that's exactly what we want, right? We want to say, right, first, we want to do filter, and we want to keep only things that are less than 10, right? So we could say something like lambda x is less than 10. Again, I think we've seen this, but I don't recall. We can also write this as this idea of like having a function that just applies some operator to the argument of the function and some other constant is a pretty common idea. So you can, if you put it in parentheses, an operator in parentheses with a single argument on one side or the other, that is a function that's waiting for the other argument. So less than 10 in parentheses is a function that says you give me an argument and I'll see if that thing is less than 10. Okay, so that's the first part of what we want to do. The second part is multiplying everything by 2, right? And that's just map. So we just want to do map. And again, I could write, you know, lambda x times 2, but it's more idiomatic to just say map times 2. Right? And so I don't need to pattern match on the input list, right? Because map and filter are going to do the pattern matching for me. It doesn't matter what the input list is, I want to do filter and then map. So I could just say do stuff to x's equals, well, I'm going to map times 2 filter less than 10 x's. And there's actually a way I can write this even more simply. I think we've talked about this. Can you remember a way we can simplify this? Is it familiar? Yes, exactly. So like what I'm doing here, I'm putting x's into a function, and then I'm taking the output of that and putting it into another function. So I could just say, so I'm going to map times 2 compose filter list. That's it. So this is like the final nicest version that I know of. Way to write this. I hope you like this as much better as than the Java as I do. You know, and why? So why is this better? Well, number one, it's shorter, of course. That's nice. It also, right? It doesn't have to talk about. It doesn't have to give names to stuff that we don't really care about. So, like, we don't have to talk about indexes I. We don't even have to talk about, you know, x cons x's and stuff. It's really not even. Actually, it doesn't use any names at all. Right? It just says, yeah, do stuff 2 is the function that first filters and only keeps things less than 10, and then it multiplies everything by 2. Doesn't like I don't have to give names to anything. It separates out, like the different pieces are, you know, these kind of nice library functions that we can reuse in other contexts. Right? I didn't have to like write some special code that like mixes up the things that I'm doing. You might worry remember with the Java version, we said, oh, we could do it this way, but we'd have to make it like another array list to go in the middle here, and that would be inefficient. And so, in some sense, yes, this Haskell code is, this filter function is going to produce a new list, which the map is then going to immediately take and like produce yet another list. So you might worry that this is inefficient for the same reason. But it turns out because this is such a common thing to do, and it's encouraged in Haskell, people have worked really hard and put a lot of effort into optimizing this kind of thing. So, in fact, if you have optimizations turned on, compiler optimizations turned on, like the actual final code that gets generated for this, there will not be a list that gets generated in the middle. It's going to, like in practice, it's going to take the input list and just directly, on each element, it's going to like check if it's less than 10, multiply by 2, and put that in an output list, kind of. Because this intermediate list, like it gets created and then consumed immediately, so it can see that and it can like just get rid of it. So the actual like assembly code that gets generated would actually be, just a little loop that's going through. It's going to be pretty efficient. So, cool. Any questions so far? Right. The other thing I wanted to point out about this, I just remembered. The other reason that it's able to get rid of the list in the middle is because of laziness. So. Right, so imagine thinking about Java again for a minute. Right, Java is not lazy. That means whenever you call a Java function, the arguments to that function have to be completely evaluated before you call the function. Right, so if I say f parentheses g parentheses something, it has to first call G and completely finish executing G and figuring out what the output of G is before it calls F at all. Right? That's kind of what a strict language means. And so if that were the case in Haskell, then it would really need to make an intermediate list because, this is function composition. So eventually it means the input to map times 2 is the output of filter less than 10. And if it had to completely finish evaluating filter less than 10 first, right? That would be given some input list. It would have to completely evaluate it, filter everything, and produce a list. And it would then hand that list off to the map, right? That's not how it works, right? Like when we call this, let's say we call this on the command line, on the Haskell prompt, and we say. We just want to print out the answer, right? It says, all right, we need to print out this list. So what's the first element of the list? It's like, well, this list is defined as a map of something. So it's like, okay, hey map, what's the first element of your output? And map says, well, okay, I need to know the first element of my input. So it says, hey filter, what's the first element of your output? And filter says, well, let me go look at my input. And it gets the first element. Filter figures out, just enough to know what the first, let's say the first thing is less than 10. Filter says, yeah, okay, 3. That's the first thing in my output. Filter is now kind of paused, right, and hands the 3 back to map. And map says, okay, 3 times 2 is 6. That's the first element of my output. And I'm going to wait now until someone needs to know more. And then, the prompt can go ahead and print out the 6. And then the prompt says, okay, now I need to know the second element. And then we kind of go through that process again. I mean, conceptually. it's more efficient than that. It's not literally like, you know, going back and forth every time, but the point is, because these actually are kind of executing, they end up kind of executing in parallel. It doesn't completely do this and then completely do this, right? As you need to know more things, each of them is like executing a little more to get each part. And that will lets us do things like, you know, if I just want to say take 5, I only get the first 5 things, and then they just say, okay, forget the rest. They never actually bother, you know, filtering or mapping the rest of the list. But that also means that there doesn't need to be, because they're only ever like kind of, you know, filters only ever giving one thing to map at a time. It doesn't have to compute the entire list and then hand that to map. And so we don't actually need that list in the middle at all. So I guess the big takeaway here is that laziness enables Haskell code to be more compositional. What I mean by compositional is that we can build it out of little pieces, you know, like this, and we don't have to worry that it's going to be inefficient. In a strict language, you have to worry about that because you have to do things like what's done in this Java code, because your only other alternative is to make an entire intermediate array list, and you know, first put stuff in that array list, then put stuff in the second. Right? I mean, essentially, what we're doing here is kind of what ends up happening in the Haskell code. You know, for each index, we're filtering and then mapping all at once, right? Kind of thing by thing, as opposed to doing all the filtering first and then doing all the mapping. In Haskell, there's kind of no difference. You can write it as if you're doing all the filtering and then all the mapping. Conceptually, that's what you're doing, but operationally, when it actually runs, it's kind of interleaving them so it can be more efficient. Okay. Let's see. Let's do another example. I'm just making this up. We're gonna take as input a string representing a sentence, and we're going to count. Let's see, what am I do? Convert, or I'll say get rid of. Count the number of unique words in a sentence, ignoring punctuation and capitalization. So, for example, if we have this string like hi there. This should say 1, 2, 3, 4. There's 4 unique words, right? Hi, there, you, and go. And you know, this there and that there are the same because we don't care about the period, we don't care about the capital T, etc. Okay, does that make sense? Or again, this is kind of artificial, although not quite as artificial anymore, because like you can imagine wanting to do this. Or certainly the idea of processing some input and like ignoring capitalization, whatever that. So this should say 4. Or actually, you know, instead of saying count, let's just say return a list of unique words in a sentence. So this is not going to be harder, it's actually be easier, so you don't have to. I wanted to return something like this. All right. So how are we going to do this? You know, if you were going to write this code in Java or Python, you might immediately think about, okay, well, let's see, I guess I need to write a loop to go through the whole string, and maybe I'm going to keep like a, you know, a map or a set of words that I've seen. And as I go, if I see a space, then I'm going to like reset some booleans that I know that now I'm looking at a new word or something. And every time I see a character, I'll lowercase it. And if I see a punctuation, I'm going to ignore it, right? So, but that's, so number one, that's a very kind of imperative way of thinking about it, of like going through each thing one by one. It also means you're mixing up all those things. You're mixing up all in one giant mess of code in one loop, right? All the stuff about like ignoring punctuation, thinking about where the spaces are, capitalization. You have to do all that stuff like all in one thing. And you have some data structure that you're like mutating as you go through to keep track of those. So obviously we're not going to do it that way. We're just going to think about, all right, what's like, can I take this initial string and transform it through a series of steps until at the very end I get that? Okay, and I'm just going to like, what is like the simplest step I could take to transform it a little bit closer to what I want, right? So our goal, transform the input through a series of simple steps into the desired output. So can anyone think of like what may be a first step that might be helpful? And there's not just one way to do this. And don't worry if you know how to do this thing and you're going to say in Haskell or not. Just say, well, this might be a simple transformation we can do, kind of conceptually. What do you think? What would be like a first step to take this string and transform it into something that might be closer to what we want? Silas? Just lowercase everything? Sure. That's great. So one lowercase everything. I like it. Okay? What should we do next? Sammy? Okay, so we can split it into words. Jack?
Remove the punctuation.
Okay. Yeah, and why don't we do that before we split it into words? I think that'll be probably a little easier, right? Because then once we split it into words, then we have to go through each word and remove punctuation. But remove punctuation. Okay. Then what? So now we've got a list of words, but they're not necessarily unique. Silas?
Filter it on, I guess you can put non-repeating.
Right. Well, I can't filter it, right? Filtering that specifically for talking about like this function. It just takes a predicate that says, look at one word and tell me whether you want to keep it or not. But I can't say like, oh, have you seen it before, right? Yeah, no, because it's just like looking at each thing individually. So I mean, yes, we definitely want to do that, but we can't do it using the filter function.
Is there a pair function?
Yeah, well, sure, we can ask if things are equal. Yeah. Jack?
Is there like a contain function?
Yes. Yeah, it's called element. How would you use that?
I'd say if there's a way to keep a list variable.
Yeah, so, yeah, I mean, so we could say, all right, I'm now gonna like go through the remaining list one by one, and I'm gonna kind of keep track of a list of things that I've seen, and each thing as I see it, if it's in there, I'm gonna throw it away, and if it's not in there, I'm gonna add it to there and like keep it. We could do that, but now, right, we're back in the world of where like we're writing our own like explicitly recursive function to go through the list. We're kind of keeping track of this variable. It's kind of like we're keeping this beautiful variable. We're updating it as we go. So I want to see if we can think of a different way to accomplish it that is still kind of thinking on the level of working with the whole data structure, not processing things one by one. And actually, so I'll give you one hint. I mean, there's different ways to do this. There's a way that I have in mind, but one hint is that actually I don't care, or let me say this, the problem is easier if we don't care what order we get the words out at the end. If we care about keeping them in the same order, then we're kind of stuck doing what Jack suggested, because we kind of, we need to make sure they stay in that order. If we don't care what order they're in, it makes things, we have some other options. Yeah.
You mean order as in alphabetical or?
Well, no, I meant like like, the way I wrote this, these four words are in the same order that they were in the sentence. But maybe I don't care about that. Maybe it may be in alphabetical order. So, maybe yeah, so maybe it's like this, right? This is fine with me.
Do like we did in that one of the homeworks, sort it alphabetically, I guess,
Okay.
and then split it, like the 3 highs and the 2 theirs, and then you go.
Okay. Yeah. So I like that. So you're saying if we sort the remaining words alphabetically, and actually, this is a bad example because maybe I'll change it like that. It was a bad example because the words were already grouped together. So, yeah. Okay. So Alexandria is saying let's sort it first. That way, all the identical words will just be right next to each other in the list, right? So if we sort the whole thing, sort alphabetically. And then you're saying split into groups of identical words. Yeah, and there actually is a function that will do that for us called group. And then what? So now we have something like, we have something like this, yeah, something like this, right? By itself. Yeah.
Do we just pull the first index from each list?
Yeah, I like it. First. Yep. That's it. Again, there's other ways you could possibly do this, but this is one nice way to do it. So let's write this in Haskell. So I don't know what to call it. So it has type string to list of string. And I'm just going to write it from the get-go as a big function composition, right? Because this literally is going to be like 6 functions that we're just composing in a big chain. The only slightly annoying thing about this, again, thanks to Euler or whatever, hundreds of years ago, we have to write it backwards, right? Because like the input goes in over here, and then the steps are going to go, like step 1 is going to be on this end, step 6 is going to be here. It is what it is. I'll just like, I start writing I'll still write step 1, and then I'll like move the cursor in front of it, and then like put a dot, and then put step 2 in front of that. Also, like sometimes when there's also an operator in the control.arrow library that looks like this, like a triple right arrow, and it's basically function composition but backwards. And so you can actually write them left to right. I do that often if I'm just like, I'm solving competitive programming problems in Haskell. I want to just write code really fast and I don't care who's going to read it. I wouldn't write code that way. A bunch of other people are going to look at it because it's not as common. But all right, so step 1, to lowercase everything. How do we do that? Well, what was that? Call some lowercase function. Yeah. So yeah, good. So what do you want to search for?
A string. Just type in lowercase.
Oh, lowercase. Yeah, this is actually not. Yeah, that's actually surprisingly unhelpful. I thought that would work. So like this looks promising, right? But this is actually in like this package called Extra, which is not like a standard package. Convert a string to lowercase. Yeah, that is what we want. Well, we could look at this and be like, well, how is this different? Where's the source? Oh, map to lower. So yeah, I mean, one thing you realize is like, okay, a string is just a list of uppercasing everything, that really means we're doing the same thing to every character. So maybe there's a function to convert a character to lowercase. And there is indeed. And I don't know, if we just search for char or charm, there could be a lot of things to that type. Actually, yeah, 2 upper, 2 lower, those are the first results. So this is in the data.char module, so we can import that. Okay, so map to lower, that's our first step. And then I'm gonna, put an underscore here. Saying, well, you have to, list of char, that means string. We still have to turn a string into a list of string. What's step 2? Remove punctuation. How do we do that? Yes, Amy?
I'll use all filter, some function checks.
Right. That's right, yeah, so we did, it's definitely a filter, right? Because strings are just lists, so I can do filter something. And now, okay, how do I check whether something is punctuation? There's probably a function to do that. And we could either try searching for it. I mean, like I could try searching for char to bool. Actually, no, this is not bad. Is control, is space, is lower, is upper, is alpha. There's a lot of is letter. Is punctuation, there it is. Another tactic we could have chosen is just like, I already knew we were using something from this I found this data.char package, and like it's probably in there. Let's just look in data.char and just like look through and see like, oh, here's all these is functions, and let's like search through the page, do like a find on the page for the word punctuation. Okay. There it is. It's punctuation. So I want to filter. So do I want to say filter is punctuation? Yeah, not is punctuation, right. So like this. Okay, why is he yelling at me? Well, no, this is how you do not. The word not is couldn't match expected type bool with something. Yeah, so not takes a bool, right? Is punctuation is not a bool. It's a like char to bool function. So what do I actually want to write here? Sammy?
Right, product is
Yes. I'm saying, we're going to take a char, put it into its punctuation, that gives us a bool, and then I'm going to take that bool and pass it through not. Okay? Split it into words. There's a function called words. Does that. Now, I want to sort alphabetically. Perhaps surprisingly, there is a function called sort. Does that, but it's in data.list. What next? We're going to split it into groups within the board, so there's a function called group. Oh, that's also in data.list. So group, it takes a list of arbitrary things and it just splits them up into consecutive groups of things that are all equal. So, like if you have like 1, 2, 1, 1, 2, it's gonna just have the 1 and then the 2 and then the 2 ones and then the, right? So only like adjacent things. This is why we had to sort it first, right? Because group isn't gonna group everything together. Only things that are already next to each other. there's also like a function called group by, where you can give it a function that kind of tells it how you want to group things. You don't, so by default it'll just use normal equality, but if you want to group on some other characteristic, you could give it a function. All right, and then what's the last thing? Okay, we're going to only keep the first word of each group. How do we do that? So the word each should take off, and maybe there's some kind of map happening. So I'm going to do something to each list, and the thing I want to do to each list is to get the first element of the list. So there's a function called head that will do that. Now you should not use head normally, because if you call it on an empty list, it'll crash. Okay. So typically, if you're using head, you want to think, do I really want to use this, or do I want to like pattern match on the list or something? In this case, this is one of those cases where it's actually okay, because group will never return empty lists, so it will always give us like non-empty groups of things, because if it's empty, there would be nothing there to group. So we know that in this